Hi everybody, welcome to another amazing episode of the ASGCT 2026 Soundbites. I'm your host, Dr. Casy. I am one of the committee members for the Communications Committee, and here with me today is the amazing Dr. Dawn Bowles from Duke University, and she's here to talk to us about her career and some of the amazing things that she's accomplished so far. Dr. Dawn, how are you? How's the conference going for you so far?
I'm doing well. Thank you, Casey. Thanks for inviting me. The conference is really amazing. It's overwhelming. We were just talking about this earlier. The first time I ever came to an ASGCT meeting was actually when it was ASGT. Is that right? American Society, GT, not without the C.
Mm-hmm.
And it was actually in Boston here in 2002. So, it's good to be back.
Yeah, it's been...
in a different, larger venue and a tremendous, increased number of people here. It's just amazing how many people are at this meeting, and it's just overwhelming the amount of information when you compare, this meeting to over 20 years ago, to the meeting over 20 years ago. Yeah, it's amazing.
So you are someone who've done so much in your career, and it's very impressive. One thing I want to talk to you about is the very first AV engineered AV capsule that's made it into the clinic, AV 2.5. Can you tell us a little bit about the process behind how it came about?
Yeah, so this was before AI. I mean, we were doing, we had very little information at that time. We had sequence information about different serotypes 1 through 6, and then 7, 8, and 9 came into play. And it was very early on looking at, the transduction profiles of these different serotypes, and there were some that were more readily transduced the skeletal muscle than others. And so we really did some very rudimentary alignments, looking at amino acid commonalities and amino acid differences between these different serotypes, aligned with their phenotype of what they did in animal models. Around the same time, the AAV structure information the crystal structure became available, and that really led to at least a confirmation or guidance. It was able to guide us into really what areas of the capsid should we focus on to make these rationally designed changes. And I remember, I think it was like in 2002 or 2003, it was Joe Rabinowitz who was in the lab, Josh Grieger who was in the lab, and we went to Florida and met with Mavis there, and had a wonderful time interaction with her. She took a look at what we were thinking about, and she sat there, we sat with her, and she did all this modeling, and that's really how this collaboration came about, and guided the design of the 2.5 capsid. It was really fun times there at that time, and again we were doing things without AI.
Yeah. I can only imagine being in the presence of Mavis Abenji McKenna at the time.
Yeah.
What was that like the interactions like?
It was amazing. I mean, she was just so humble, so kind, so smart, so brilliant. The field is just, lost so much with her loss, but she contributed so much to the field. It was just amazing.
That's awesome. Now, again, you've done so much. One thing that I also want to talk about is, I want to say your new work, not so new really, about heart transplant. Can you tell us about what you are doing exactly and why it's important?
A lot of my work now has been focused on cardiovascular disease, heart failure, and heart transplantation. And heart transplantation really is the gold standard treatment for end-stage heart disease. It's a good therapy, but it's not a perfect therapy. There are negative effects, from heart transplantation. Most of this is due to long-term immunosuppression. So when you have an organ transplanted, you're always at risk of having rejection. So you're on these medications for the rest of your life. They suppress your immune system and enable your body to tolerate or accept, that organ and not reject it. But you are at a risk you're immunosuppressed, you're at a risk of infection, life-threatening infections. You're also at a risk of developing malignancies and cancer. And really that's what a lot of these patients do die from, is not, the rejection itself, but it is something from the downstream effects of the immunosuppression. So what we really want to do in the lab is to improve outcomes for heart transplantation. One of the lowest hanging fruits that we are working on right now is actually to genetically modify or to overexpress, a protein that would influence the immune system that would kind of make the heart a less likely organ, for rejection. So what we've done for the past 10 years or so is a lot of proof of concept studies where we've been using ex vivo organ perfusion. So transplantation is really so amenable, to this kind of concept of gene therapy where you take an organ, out of the donor, and we've been using clinically utilized organ perfusion systems, and this is all experimentally. This is all experimentally right now in pigs, in our pig models. But you can put the heart onto these devices, and then you can perfuse the heart with a solution. Sometimes the solution is blood-based. Sometimes in other systems it's non-blood-based. But then you can put the heart on these devices, and then you can add a viral vector or any really kind of advanced therapeutics to the system, to the circuit, and perfuse that organ for a relatively long period of time. We use 2 hours in our experiments, but clinically these hearts are being stored up to about 9 or 10 hours and still transplanted. So we've done a lot of proof of concept to demonstrate that you can get very efficient vector transduction. We've used adenoviral vectors at first, and then we've used different serotypes of AAVs, and demonstrated you could get with the AAVs up to, we've only gone up to 120 days, but you see very, very robust transduction. It's only in the heart. It's nowhere else. There's no evidence of gene expression or vector DNA anywhere else in the body. So it's very safe. It avoids toxicity issues with getting the vector in the liver. So we've done a lot of that work, and at the same time we've been working to develop a porcine model of acute cellular rejection. So we published that last year, and concurrently with that we've been doing a lot of mouse studies where we've been looking at different transgenes in mouse heterotopic heart transplant models to determine what therapeutic are we going to go forward with. And so all of this is converging right now, and we're about to start a study, a preclinical pig study, where we will be testing our therapeutics in the context of this pig rejection model, and then also utilizing these clinical devices at the same time. So knock on wood, we hope that we're going to have positive results, and hopefully in the future move that to a clinical trial.
So that's exciting. And how long will it take for us to see this in the clinic, and what would it take? Right?
Yeah, that is an excellent question. There's still a lot of unknowns from a dosing standpoint. We really don't understand. Even if we do have a good transgene, we still have to do a lot of dosing studies. This is going to be an ex vivo delivery, so I would hope that the path would not be as stringent as the path forward with in vivo delivery. But right now I'm just kind of laser focused on getting this preclinical trial done and see what the results are.
One step at a time, right?
One step at a time.
And another big news that came out recently is that you've been awarded a nice grant from the NIH, right? Can you tell us what it is, what it's about, and what you hope to accomplish with it?
Yeah, this is also a collaboration that has been ongoing for quite some time at Duke with different investigators. specifically Laura Hale and Joe Turek at Duke. And this builds on the work of Louise Markert, who developed a thymus transplant strategy, cultured thymus transplants for DeGeorge disease, which is, babies are born without a thymus and basically they don't have an immune system. And so what Louise did, she did this pioneering work where she was able to slice and culture thymus and keep the thymus in culture for a period of time, and then implant these thymus into children who had no thymus, and basically demonstrated that you could reconstitute their immune system and treat this disease. This led actually to a product. It's called Rethymic. It was in Savannah. I'm not sure what the name of the company is now that has this treatment. But one of the problems with the thymus culturing and engraftment is that it takes about 5 or 6 months in order for the thymus to fully reconstitute and for you to start getting T cells to come from that thymus. And so what this particular grant is focused on is using gene therapy that's delivered to the cultured thymus, and it's providing different molecules that would allow the thymus to reconstitute quicker once implanted. Yeah, so wow. It's an R21. It's a high risk, high reward. Yeah. It has a lot of potentially direct application into further improvements on that treatment.
Wow, this is incredible. This is awesome, man. This is awesome. So what's next after that? Right? What's next? What else are you working on?
What else am I working on? Yeah. A lot of my work is recently, or for quite some time, has been establishing the Duke Human Heart Repository, which is a biobank of human specimens from many cases at Duke. I'm in Duke surgery, and I've aligned with a large number of Duke surgeons, and we really are trying to really understand these different etiologies of heart failure, doing a lot of multi-omics assessments of the tissues, really trying to understand, pathways that can use, targets that we can use for gene therapy, pathways that might be amenable, for gene therapy that may lead to some therapies for different types of cardiomyopathy. So that's a lot of discovery work that we're doing right now, but we feel that it's going to bear some fruit in the future.
Oh, that's awesome. I'd like to ask another question, if that's okay.
Sure.
I want to know, did you know, 5-year-old Dr. Dawn Bowles knew that she would be doing what she's doing right now?
Oh, no.
No?
Not at all. No. I wanted, actually, when I was a little girl, I read a lot of detective novels, Nancy Drew, and I really wanted to be a detective. And I guess in kind of a way I am. We are, trying to solve, mysteries. And maybe I did know, and it's all a mystery that we're all trying to work on and solve.
That's awesome. All right, there you have it, folks. Thank you so much for stopping by, and I hope you all enjoy this amazing episode.